Hi guys, my name is Shirag Shemmassian and I'm an MCAT tutor at Shemmassian Academic Consulting, and today I'll be walking through a chemistry passage from the Chem Phys section on the MCAT. Thank you so much for joining me. I hope that some of the strategies that I go over today can be helpful for you when you take the exam, and just absolutely kill that first section so that it sets your confidence and your mood high and right for the rest of the exam. All right, so let's jump right in. So just to start off, you can see here on the screen that I've kind of set up this background that's similar, that is similar to what you'll see on the actual MCAT. And I do that to remind myself to simulate test conditions as much as you can when you practice. Practice is super important, but it's also the way you practice that matters. So you want to make sure that you are in a quiet room, you're isolated, there's no distractions, you're really zoned in, you're really in that MCAT zone that'll help you do your best on your practice and then also do your best on test day. So whatever it is that you need to do, whether it's tell the people that you live with or go to the library or something, just make sure you're doing your best to make yourself and your surroundings as similar as you can to what you'll experience on test day. So that really helps, and that's my number one tip always. All right, and so for this passage, typically you can take about 8 minutes for a chem passage. I'll be walking and talking through it, so it'll take a little bit longer and showing you guys some highlighting strategies and just ways to understand the material a little bit better for when you're actually taking the exam. So let's start reading this. Most biochemical reactions depend on the pH value of the aqueous environment, and many are strongly favored to occur in an acidic environment. All right, so that seems important to me. So I'm gonna highlight acidic environment. A non-invasive control of pH to tightly regulate such reactions with defined start and endpoints is a highly desirable feature in certain applications. All right, so let's pause here. Something that I always like to do with science passages is simplify, simplify, simplify. Anytime I read something, I want to bring it back to stuff that I've already learned about, concepts that I'm familiar with, and just kind of gut through all the verbiage that the AAMC puts in there to get at what is the core of what they're saying or the core of this study. And what do we need to know, right, to best answer these questions? Because that's what it comes down to at the end of the day. It's not being able to, write the best summary and detailed mechanisms of what's going on in the study, but it's simply just to answer the questions. So putting that into practice here with this first little section, the main things that I'm taking away from this is that there's going to be some sort of reaction, and we're going to be dealing with it in an acidic environment, and probably going to be talking about how pH functions in controlling the way reactions and mechanisms work. So just off the bat, I'm thinking about pH, acidity. That's it. Nothing too complicated. So let's keep reading. Researchers report a novel optical approach to reversibly control a biochemical reaction by changing the pH and using acid phosphatase as a model enzyme. All right, so acid phosphatase as a model enzyme. Okay, so I'm assuming acid phosphatase will be a molecule that we're going to be learning more about, so I'm just going to highlight it. The reversible photoacid G acid functions as a proton donor, so that seems like another player in this reaction, so I'm going to highlight G acid, proton donor, which we already knew because acid is in the name, and acids donate protons to make the solution more acidic. Okay, changing the pH rapidly and reversibly by using high-power UV LEDs as an illumination source in the experimental setup. So I guess the LEDs, this is where kind of this optical comes into play here. We don't know if that's important or not. Seems like it could be, so I'm going to highlight it for now, but not too much, not all over the place. Okay, the researchers found that the reaction can be tightly controlled by switching a light on and off, making the technology applicable to a wide range of other enzymatic reactions, thus enabling miniaturization and parallelization through non-invasive optical means. Okay, so sounds like they're talking about how light functions here and how it can be applied to things outside of the study, but that does sound like it's outside of the study. Sounds like it's kind of specific. I don't know how useful that'll be for us answering these questions. I'm not going to think too much into it. I mean, I don't really even know, to be honest with you, what miniaturization, parallelization are. So I'm not going to let that trip me up. I'm going to keep moving. And if there's a question on it, we'll come back to it. But if not, we're not going to spend any more time trying to figure out what that may be. Okay, so figure 1 displays the structure of the G acid. So here's figure 1. Looks like it's showing us what the G acid looks like. I'm going to take note. It has, sulfurs, oxygens, hydroxyl group, benzene rings, reacting with water. And it is a G acid, so it is donating a proton, as we can see, to the water. So if this is the acid, looks like water is the base in accepting this. Let's put the base over here. In accepting this proton, because from content review, we know that proton donors are acids and proton acceptors are bases. So great. Okay. In order to use the photoacid in a wide range of biochemical applications, the researchers ensured that it met certain requirements such as solubility in water, low toxicity, and excitability with commonly available and expensive illumination sources such as LEDs. LEDs have several advantages compared to more conventional illumination sources. They are more efficient, have a long lifetime, a compact size, and high reliability. Okay, so this kind of just gave us a bit more information about the photoacid, about the optical nature of this experiment. Again, not sure how relevant that is. Seems to be just going a little bit more into the mechanism of it all. It's good to know, but I don't think we need to think too much into it at this point. So let's keep going. And that's one thing, I want to emphasize always on the MCAT. If anything does seem confusing to you and you're like, oh my God, I'm completely lost, don't get stuck on it. Keep going, because you never know. In my experience, I've read a bunch of passages where I'll spend 5 minutes trying to figure out what that apparatus is or how it plays into the whole experiment. And I'll read the questions and I find that they didn't even ask a question about that. So I didn't even need to spend all that time. So would hate for that to happen to you. Just keep going, read the passage once, get a general understanding of it, and then go to the questions. Always my tip. Okay, the researchers chose an acid phosphatase. Okay, here's that acid phosphatase word again. I'm going to highlight that as a model enzyme to further study the system. Okay, so it looks like we're going to be using acid phosphatases in this study. It's going to be the focus, so I'm going to zone into that. The activity optimum of APs, I'm assuming that's acid phosphatase, typically lies at an acidic pH, there's that acidity again, of 4.5 to 5.5. And so this is the activity optimum. And we know that enzymes do generally have an optimal range of pH that they work the best at. So again, this 4.5 to 5.5 range is in line with what we've learned about this already, that it works best in acidic environments. Okay, acid phosphatases, APs, non-specifically catalyze the hydrolysis of monoesters, so hydrolysis of monoesters to produce inorganic phosphate under acidic conditions. All right, so looks like when we use APs, inorganic phosphates are going to be part of the product. Just something to keep note of. In experiment A, okay, so now we're getting to an experiment. Researchers used the acid phosphatase from potato, EC 3.1.3.2. Okay, so I'm just going to highlight that name. So if they ask a question about it, I know where to find it. And it's an acid phosphatase. And it's active between pH 4 to 7 with an activity optimum. There's that activity optimum again, at a pH of 5 to 5.3. At an alkaline pH of 8, the activity of this acid phosphatase is several orders of magnitude lower. Okay, so what I'm gleaning from this little paragraph here is that there's a study with an acid phosphatase that works best at this pH range of around 5 to produce inorganic phosphate. That's just kind of my one sentence summary of what we've learned of this experiment so far. Okay, to assay the EC 3.1.3.2 activity, researchers used p-nitrophenyl phosphate, p-NPP assay. The PNPP assay is a calorimetric assay in which the substrate PNPP is hydrolyzed by acid phosphatase into the product PNP plus inorganic phosphate PI in purified HPLC grade water as shown by figure 2. All right, so looks like there was a reaction done here that can be summarized quite neatly by this figure. Looks like our acid phosphatase is doing exactly what we just read that it does, cleaving monoesters into its product and inorganic phosphate. Okay, so that's the study. And it looks like at this point, if I were to kind of make note of a few common main themes, I would think maybe acidity. I would think about inorganic phosphate. I'm gonna shorten that, inorganic phosphate, and then also would think about maybe like proton donors, acceptors. Okay, and again, maybe you jotted down a couple different main ideas, but if you can understand the passage well at this point, that's great. But again, we just want to make sure that we're getting these main ideas down and a general understanding of what it is that the questions might ask about. Okay, so let's go to the questions now. Let's keep moving. Let's read the first question. Which of the following best describes the role of water? And again, I encourage highlighting in the question. I find that it helps me a lot. Role of water in the deprotonation of the G acid. So before I even read the answer choices, I'm immediately thinking about what the question is asking. Deprotonation of the G acid, where did we see that in the passage? We saw that in figure 1. We already wrote down earlier that there's the G acid, there's water, and it looks like this water is acting as a base. We wrote that down earlier already. So what we can do at this point is we kind of have an idea that water is probably a base. And it looks like, yes, that's right there in the answer choices. But let's look at the other answer choices, make sure we're choosing the right one. So A, acid, that's probably not it, since water is reacting with G acid, which is already an acid, and it's accepting a proton from G acid. So we know that acids don't accept protons, they donate protons, similar to what G acid is doing. So we can cross out A. Catalyst. So catalysts are molecules that are used to lower the activation energy of a reaction. This reaction doesn't mention anything about activation energy, and water is also not regenerated in this reaction. So for that reason, we can cross out option B. And so now we're between base and aprotic solvent. So water, as we know, is definitely not an aprotic solvent. It's a protic solvent and has 2 hydrogens right there. So we can cross out D as well, leaving us with C, base is the right answer, which is what we thought originally as well, but doesn't hurt to go through your other choices and make sure you're choosing the right one. All right, let's keep going. 2, the researchers measured the energy of a photon during an experimental trial to be 3.3 times 10 to the negative 12 joules. What is the frequency of the wave? Note Planck's constant is equal to 6.6 times 10 to the negative 34th. Awesome. Okay, so this is a physics question, and you might be thinking, oh my god, we're in a chem passage. Why are they giving us physics questions? Well, that's because we're still in the chem phys section of the MCAT, and even though this has basically nothing to do with the actual experiment, the MCAT is always going to try and test you on a holistic range of topics. So always good to still be comfortable with these concepts and still be ready to use this on the question. Make sure you're using your physics knowledge if it is required, which it is here. So for this, we can use this equation. E is equal to hv, E being energy, H being Planck's constant, and V being frequency. So we have 3.3 times 10 to the negative 12 joules as the energy. We have Planck's constant, which is equal to 6.6 times 10 to the negative 34th. And we know that Planck's constant has the units of joules times seconds. Joules times seconds. Okay, and that's times frequency, which we're solving for. So frequency is going to be equal to 3.3 if we divide both sides by 6.6 times 10 to the negative 34th. 6.6 times 10 to the negative 34th. We'll get that frequency is then equal to 3.3 times 10 to the negative 12th joules divided by 6.6 times 10 to the negative 34th joules times seconds. So we can cross out the joules, and we get the units already to be inverse seconds, which shows us that we're on the right track because we know that frequency has units of inverse seconds. All right, so to do the math here, you don't get a calculator on the MCAT, so you kind of just have to do it on using a pencil and paper, which you will be provided. So right off the bat here, I'm gonna note that 3.3 is 1/2 of 6.6. So 3.3 times 2 is 6.6. We can cross that out and simplify for this to be 1 and this to be 2. And then the exponents, 10 to the negative 12th over 10 to the negative 34th. The way I like to do it is I like to first cancel out the negatives. So I would convert that to 10 to the 34th over 10 to the 12th, make them positive. And then when we're dividing exponents, it's just subtraction. So you do 34 minus 12, that the 10 to the 12th on the bottom will cross out, and this exponent 34 will reduce into 22. So the final answer is going to be 1/2, where we got from here, or we can do 0.5 times 10 to the 22nd. So you could definitely convert this to, move the decimal place over, and then you made the number bigger, so you make the exponent smaller. That's a trick on my end. So you do 10 to the 21st, but probably just look at the answer choices first, because it looks like going down, all of them are to the 22nd power, and they do in fact have 0.5, which is the answer. Okay, great. So just some quick maths on the MCAT section. Always got to be ready for that. All right, question 3. Which of the following functional groups is not found on the protonated G acid? All right, so for this, I would recommend going back to the passage, looking at the reaction. This is the protonated G acid, and let's look at the answer choices. So the first one is an alcohol group. So we know alcohol group is going to be ROH. And if we go to the protonated G acid, we can see that there actually is an OH group right here. So we can cross out A. And along with that, we see these 2 big benzene rings right here. So we can probably cross out B as well. So now we're between sulfonate and sulfite. Okay, so we do see that this molecule has a sulfur in it. So we know it's, probably has to be one of those 2 options that it does have, but we have to figure out what is this functional group called. So we see that it's a sulfur with 3 oxygens, and it's bonded to the carbon of benzene. So it's bonded actually to a C, which we can call an R group. And if we look at what we typically consider as these sulfur-based functional groups, we're thinking about our acids, right? Sulfuric acid, which is H2SO4. We're thinking about H2SO3. And we notice that these sulfurs are only bonded to an oxygen or to a hydrogen. There's no R group. And so we need to find a molecule, a functional group that's bonded to an R group. And so when we look at the sulfonate, the suffix onate is different from what we usually see with sulfite, sulfate, or sulfide. And I know that sulfate is a sulfur bonded only to hydrogens or oxygens, and sulfite is a sulfur that's bonded only to hydrogens or oxygens. And so even if I don't know exactly how many hydrogens or oxygens there are, I know that it's not a sulfur that's bonded to an R group. So since this sulfur is bonded to an R group, it's not going to be sulfite. It's not falling under that category. It's probably going to be sulfonate, which means sulfonate is the functional group that's found in this G acid. And actually that's correct, because the sulfonate group is a sulfur atom that's bonded to an R group with 2 double bonds to an oxygen and a single bond to a negatively charged oxygen, which is exactly what we see here. And so the functional group that's not found on the protonated G acid is sulfite. And we can see that a sulfite group, from our review, we will learn that a sulfite group contains 3 oxygens and 2 negative charges, which we don't have. We only have 1 negative charge. And so that's why the correct answer is going to be, actually, the correct answer is D, because that is what's not found on the protonated G acid. Okay, great. So last question here. Researchers are likely to observe which of the following during a PNPP assay for EC 3.1.3.2 when pH is lowered to 5. All right, so I'm thinking about what I read about this earlier in the passage. I think I read something about it over here when they were talking about this experiment. And so I highlighted EC 3.1.3.2, the name, so I could find it easily, because it sure is a mouthful. And it says here, EC 3.1.3.2 is active between pH 4 and 7 with an activity optimum at a rate of 5 to 5.3. So if they are lowering the pH of this assay to 5, that is right in that activity optimum. So that means that this acid phosphatase, EC, is going to be at the peak of its activity. It's going to be working really hard. And so what exactly do these answer choices say? A, cleavage of EC 3.1.3.2. So we don't learn anything about cleavage of the enzyme in this reaction or in this passage. It doesn't say anything about that. Surely that could be a way the activity increases, but since we're not given information about that, we're not going to make that inference at this point. So I would go ahead and cross that out. Okay, so B, an increase in inorganic phosphate levels. All right, so let's look at what this acid phosphatase EC does. So when it's used, it looks like when the reaction moves forward, it actually does result in inorganic phosphate, which would make sense. If the enzyme is working a lot, then it probably would catalyze a lot of reactions, thus creating a lot of inorganic phosphate. So that does look like it could be an answer, but let's look at the other answer choices before we choose it. C, a decrease in sulfonate levels. So sulfonate, which we just read earlier, looks like it's attached to the G acid, which is up here, but that doesn't seem to have anything to do with this reaction, which is what we're focusing on. So it doesn't look like sulfonate would be really relevant here, so we can cross that out. Okay, and D, a decrease in this acid phosphatase activity. So from what we read that the activity optimum of this enzyme is at a pH of 5 to 5.3, which would mean that its activity is actually increasing, and choice D is the exact opposite of that. So we can cross that out. So the answer looks like it would be B, an increase in inorganic phosphate levels, which makes sense when you look at the fact that the activity would increase, so this reaction here would move forward, creating an increase in inorganic phosphate levels. All right, and that's this passage. I hope you guys really enjoyed that. If you have any further questions about any other MCAT topics, I encourage you to check out the other videos that the Shemmassian channel has. And I really hope this helped. Thank you again, guys, so much for joining me for this, and happy studying and good luck out there.